Hello again, everybody. Welcome back to this series. This is day two of the series that we started yesterday on talking about AI, and specifically, we're working towards AI in software engineering. So yesterday, I introduced the topic of this whole series, namely large language models and all these new AI techniques that are coming around. And today, I want to have like a flashback to where we came from, so that from the upcoming video we can focus more on the transformer architecture and build our way from there. So I want to take you a couple of decades actually back, and we want to start with recurrent neural networks, LSTMs, and see how we got to the transformer architecture as a timeline. And I have a couple of notes in front of me so I don't mistake the authors and the orders, for example. So, before we even had this notion of transformers or modern day neural networks, it was all about sequence modeling, and specifically, we are talking about recurrent neural networks, or as they're commonly referred to nowadays, just simply RNNs, which is the abbreviation. And the idea in these models is to process the data step by step, one piece of information at a time. Let's call it one token at a time, and each token depends on the previous ones. That's still the case. The token that's generated nowadays is still dependent on the previous ones. But it was far less sophisticated than what we have currently. That approach worked for simple contexts, but you start to face a very serious limitation when you start to try to capture these more long-range dependencies between these tokens, between these pieces of context. A couple of terms that you see being popped around in the ML literature and previous literature is concepts like gradient like vanishing gradients. You also have memory decay. There's the problem with training them, and due to the sequential nature, because there's just a limit to how fast you can train these models. And in around the late 90s, there were two authors, and I have to look at my notes here, so I'm going to butcher their names, Hochreiter and Schmidhuber. So they came up with this idea of a long short-term memory, which you might have heard of as LSTM. And this architecture was a big leap, essentially. The LSTM architecture introduced this idea of a cell state. So let's think about it as a sort of lane of memory for these models. And they also introduced this idea of a gating mechanism. So you would have an input gate, you would have a forget gate, and you would also have an output gate. And this whole idea allowed the model to decide what information to keep for itself. So it would decide what to throw away at a certain point, what it deemed irrelevant, what to output, and this essentially helped with that problem that I previously mentioned called vanishing gradients. And it helped with keeping relevant information in the loop, and it helped with preserving long-term context. And this worked for quite some time, but in like around more modern day, if we're talking about it, like around the 2015 to 2020 mark, if we're giving a ballpark, even LSTMs and more adapted versions, so to say, such as the GRU, which I think stands for gated recurrent unit. These face practical limits. So the most important thing is that they're still sequential, so they still have those problems with training. So the training cannot be parallelized. Everything has to go sequentially. And the attention, so this is the first time I'm using the word attention, and this is rather different from what we refer to as attention nowadays. So the crosstalk between long context, it was still difficult. Modeling very long dependencies, so around like, I don't know, 1,000 tokens, was still very challenging. And there were a lot of advancements on top of these attention mechanisms on recurrent neural networks, but they still suffered from the inherent drawbacks of the recurrence. And then in 2017, this is where everything essentially started to change for this topic of language modeling, was when Vaswani et al. And people in the field will probably know what paper I'm referring to. They came up with this idea of attention. Well, didn't come up with it, but they developed this idea pretty well. So the paper is called "Attention is All You Need," and that gives you an idea. So the core idea is to completely drop recurrence and convolutions entirely and rely on this mechanism that they call self-attention. And self-attention is the topic of tomorrow's video, so if you're interested in knowing what that is, stay tuned. But they rely on this idea of self-attention to model the relationships between the tokens and sequences directly. So let me give you a so like a bird's eye overview of what it is. So each token creates queries, keys, and values, if I'm being exact. And attention, what it's essentially doing, it computes how much each token should attend to the other in the sequence. So like if we have five tokens in a sequence, they decide how much they influence each other and how much the other tokens influence its meaning. Pretty abstract. There's a lot of resources out there, and I'll give a few of them in the description. But you can think of it of the tokens talking to each other and being like, how much do I contribute to you and how much do you contribute to me, in giving meaning to this entire phrase. And building on this idea of self-attention, you can start to create this idea of multi-head attention and multiple different patterns of interactions and parallels start to emerge. These ideas are all building on a lot of literature about positional encodings. We'll also get to what that means. So I don't know. So there are different architectures that have come along based on this, but the idea still remains the same. Okay, so we built this new architecture. So they actually proposed this new architecture. What's the result? So the results are that these models are really good at handling long-range dependencies. And just because of the way that this is set up, you gain massive gains in parallelism. So your training goes way quicker, much faster, and it's a lot more flexible in terms of representation. And because of these properties, so two main properties, being able to capture these long-range dependencies and also being able to train them in a more rapid manner, transformers essentially took over and became the backbone of modern AI as we know it. Okay, so in summary, we started with recurrent neural networks and long short-term memory, RNNs and LSTMs for short, and we worked our way through the history and there were limitations and why we needed to have transformers, how transformers on a high level work, and what's allowed them to take over. So during this video, I talked about self-attention, and that's the topic of tomorrow's video. So if you're interested to know more about how transformers work, please tune in tomorrow. I hope you enjoyed this. As always, if you found this useful, please interact with this video so others can also make use of this content. I'm by no means an expert in this topic at all. There are a gazillion papers out there explaining it better than I did, and more accurate, not necessarily accurately, but more in detail, more technically. So I definitely recommend you to visit these sources. In the captions, as always, I have also, or they're called descriptions rather, on LinkedIn. So in the descriptions, I've included 5 resources, as always, 2 papers, 2 blog posts, and 1 video, which you can use to learn more about this topic, and they're actually the inspiration of this video. That's that for this video. Hope to see you soon, and thank you for sticking till this part of the video. Thank you. Bye.